Good morning, everyone. We're going to continue here today in Chapter 7, so I hope midterm 3 went well for everybody. I'll have a few more things to say about it on Friday or on Monday. So back into Chapter 7 here, we're going to talk about ionization energy, but I think we probably should first start with a review of what we were talking about last time, just to kind of summarize our periodic trends so far that we talked about. Z effective, Z is nuclear charge, so Z effective is just the effective nuclear charge. Remember, that's the effective charge that's experienced by a particular shell of electrons. The electrons furthest from the nucleus experience the lowest charge because they have all the core electrons that are absorbing nuclear charge in their way. Nuclear charge is primarily only affected by the core electrons. The core electrons are the biggest impact, on the effective charge, the charge that those outer valence electrons are experiencing. So as you go from left to right, if you look from, like, say, lithium on across to neon, they share just that 1s2 core. So the core is constant from left to right. So the nuclear charge is going from lithium +3 all the way to +10 at neon. So from left to right, we get that increase in effective charge. So we get an increase in the effective charge from left to right because primarily only the core electrons are screening or shielding that nuclear charge from the valence electrons. And the valence electrons don't really screen each other that effectively. So having more valence electrons doesn't really change much. They experience a greater charge as you go from left to right across a row of the periodic table. As we go down a group of the periodic table from top to bottom, we get a slight increase. And this is coming from the fact as you go up in, as you go down from top to bottom, the outer valence electrons are using larger n orbitals. And even as you go up in orbital size, you still have all these probabilities of those electrons being relatively close to the nucleus. So it's all of these relatively, by percentage, like increasing probabilities that you still have an electron relatively close to the nucleus even as n increases. So it's really these probabilities in our radial probability distribution functions that kind of show why we get a slight increase in the effective charge. So what that means is that even if you get to like potassium or rubidium, that even though they have very large cores, that their outer valence electrons can kind of sneak and still be relatively close to the nucleus and experience on average a slightly greater charge than you might have expected. So it's not a very big increase, so it's just a slight increase from top to bottom. Now, how effective charge plays a role, I think it helps us understand our atomic radius trend from left to right really well, because as you go from left to right, you have the valence electrons experiencing a greater charge. They're going to be pulled in more closely to the nucleus, even though we have more electrons that themselves are repelling each other or trying to repel each other. So from left to right, we get a decrease in atomic radius. The idea of atomic radius is just the idea of size. So if we're thinking of like lithium versus fluorine, that lithium is going to be the bigger element compared to fluorine. We usually use their radii to compare their atomic sizes. So the greater charge, the greater effective charge pulls those electrons in more closely on fluorine, so it becomes smaller. And then the top to bottom trend, if we're comparing like fluorine to chlorine to bromine to iodine and their relative size, as you go down, you're using larger orbitals, you have more electron repulsion because you have more total electrons in that case, so then you just get the increase in size from top to bottom. So the atom size goes up from top to bottom, and I think that makes sense. We're going from like fluorine, 9 electrons, 17 for chlorine, 35 for bromine, using larger n orbitals that are larger in size, so our size increases from top to bottom. And that goes, of course, despite the slight increase in effective charge. So even though the effective charge went up a little bit from top to bottom, it's not pulling the electrons in more closely from top to bottom because there's just too many electrons, and then they're already using those larger n orbitals. Our atomic radii trends here are for neutral charged atoms. So when we're comparing atomic radii, we're thinking lithium uncharged, 0 charge, fluorine uncharged, 0 charged. When we talk about ions, we have a little bit of a different situation that comes up where when we start talking about cations have lost electrons. If we're looking at a given atom and kind of comparing the size of the atom if it lost an electron, if we lose an electron off an atom, if we take, for example, magnesium, go to magnesium plus, you get a shrink in size because you lost a negative particle, so you reduced the electron repulsions, so the size is always going to decrease when we take electrons away. If you take another electron away, the size goes down even more. And then if we happen to lose the outer valence shell electron, like if you're looking at magnesium, we'll think about this on the next slide too. As you go from magnesium to magnesium plus, Magnesium 2 plus is a lot smaller because we've gotten down to just the core then. So we lost all the valence electrons, so we're going to have a really small atom if we're comparing the size of magnesium 2 plus versus magnesium plus versus magnesium. So pretty big changes in ionic radii as we're going, thinking about the loss of electrons, decreasing the size of cations, and anions do the exact opposite. So the size of an anion is always bigger than its neutral atom. Adding electrons increases the electron repulsions, increases the size. So adding electrons is always going to lead to an increase in size. And then we have an isoelectronic series comparison that we can make. Whenever we're comparing two ions that are equal in the electron count, so an easy example is sodium plus, which has 10 electrons, F minus, which has 10 electrons as well. So these are isoelectronic. They each have 10 electrons. So they each share having 10 total electrons. There we want to compare the proton count. So we look at the number of protons. The number of protons for sodium is 11. It's the 11th element. Sodium is a 9 plus. It's the 9th element, 9 protons. So we only have 9 protons to pull in the electrons for fluorine. So it's going to be bigger. And then sodium plus, more protons, becomes smaller. So we get sodium plus being smaller than F minus. Because of the isoelectronic series. So the isoelectronic series comparison or conclusion we can make is that the size of the isoelectronic series decreases with increasing number of protons. Now we can only make that comparison when two ions share the same total number of electrons. Then we're just looking for which of those ions has more protons, more positive particles, to pull in that exact same configuration more closely. So we talked about all these things last time, so this is just meant to be a quick little summary of what we were talking about on Monday, so we can sort of then head into and see the sort of impact that effective charge, size have on ionization energy, and then the last trend we'll look at is electron affinity. So we'll define those here today. So ionization energy, the minimum energy required to remove an electron from a ground state gaseous atom or ion. The word gaseous is there just to simply have from left to right. If you go across like lithium to fluorine, you change from solid to gas. We don't want to compare these trends that have a solid to gas difference, so we just want to compare gaseous ions. So when we're looking at, for example, magnesium, we can write this reaction that magnesium as a gas going to magnesium plus, still a gas, plus an electron, that the energy for that is just given by the I1. So that's what the 738 number is corresponding to. So the delta H or the delta E of this process would be equal to plus 738 kJs per mole. There's 1 mole of magnesium. If you wanted to write this as a standard delta H, it would just be 738 kJs for this reaction. But the key is that you have to have the atom absorb energy to break the attraction the electron has to the nucleus. So this has to be an endothermic process because the electron is attracted to the nucleus. So it requires a lot of energy to remove this atom, or remove this electron from this atom. If we want to remove a second electron, the I2, the 1451 number listed for magnesium, corresponds to this particular reaction of magnesium plus is a gas, going to magnesium 2 plus, still a gas, losing that electron. That's our I2. So the delta H, or the energy of this process, is plus 1,451 kJs per mole. So this is coming from the I1. This is coming from the I2, the second ionization energy. So we were talking about this last time just to kind of reinforce by writing these reactions that we can write these reactions, and like the second ionization is just the energy to remove that second electron. It's not the energy that it takes to remove both the two electrons, just that second electron. If you want to calculate the energy it takes to go from magnesium gas to magnesium 2 plus, you have to treat this like Hess's law and just add the two reactions up. I'm not going to do it, but if you wanted to calculate the energy it takes to remove both electrons, it's going to be 738 plus 1451, so a little bit over 2100 over 2100 kJs per mole. Now, when we get to I3, if you notice I3 is tremendously bigger, well, this is getting at, and even the whole thought of each successive electron removed takes more energy than the previous. Should make a lot of sense when we think about what's going on. Let's think about the 12 plus of magnesium. We have the 1s2, the 2s2, the 2p shell. I'll just draw the 2p orbitals. I'll leave out the third. And then we would have the 3s. So within magnesium, we'd have 2 electrons within this 3s shell here. And so if we remove one of these electrons, and it's been removed from the atom, we now have 11 electrons. Those electrons experience less repulsion. The electrons repel each other. So the remaining electrons can get closer to the nucleus. So the magnesium plus size, the radius of that atom, of course, like we were talking about with our radii, becomes smaller than the radius of just the magnesium atom. So taking an electron away makes the atom smaller. Then we kind of come back to that equation. Remember Coulomb's law, the energy of electrostatic attraction is equal to kappa Q1 Q2 divided by D. So if we make the distance of those electrons to the nucleus closer together, make the radius smaller, what we're doing is giving the magnitude of attraction, making that magnitude higher. So the electron that's left over from magnesium plus, that outer valence electron, is closer to the nucleus, and then therefore requires a greater energy to remove it. It has a greater energy of attraction that has to be overcome. So it's really just the loss of size of magnesium plus compared to magnesium that leads to the increase in the value of I2. And this happens for every single case where we go from I1 to I2 to I3. Each successive ionization will always take more energy than the previous. But then when we finally remove a valence shell electron, if you notice there's a big increase. Well, think about what I was saying earlier, that when you finally remove that last valence electron, the size of magnesium 2 plus is going to be a lot smaller. You can even maybe think of writing a second less than sign, that magnesium 2 plus is now going to be a lot smaller than magnesium plus because we've lost the entire valence shell. We're now just down to our core. So we're now just down to the remaining core electrons. So we have a much, much smaller size from magnesium 2 plus. Therefore, those electrons are going to be much more attracted to the nucleus, therefore a lot harder to remove. So we get a big increase in this ionization for the removal of the first core electron. Like if you continued removing core electrons, it would take successively a lot more energy to remove those core electrons. And so we can write the third for magnesium would just be magnesium 2 plus as a gas going to magnesium 3 plus gas plus an electron, the delta H here being plus 7733 kJs per mole. And that's much bigger just because we're now removing a core electron. So if you look at aluminum, aluminum has 3 valence, so it's the fourth that's a big jump. So notice we get a big jump for aluminum at the fourth, for silicon at the fifth, etc. So whenever we start removing that first core electron, large increase in ionization energy because now we have a much, much smaller ion, much, much harder to remove one of those core electrons. Now, another thing that kind of stands out here is the fact that we've talked so much about landing in that noble gas configuration being more stable. If you notice, it's actually, we don't see that here. There's nothing particularly quote unquote more stable at stopping at magnesium 2 plus or stopping at sodium plus. There's something else that has to be going on here, because it takes energy. It's not like we get to the noble gas configuration and that was more stable or negative in energy. It still takes energy to remove these electrons. The key is going to be in chapter 8 where we start to think about, well, once you make the cation, what about the anion that's made in the process by the loss of those electrons? And then what about the subsequent electrostatic force of attraction? So the reason why any sort of chemical event ever takes place isn't because of one detail. It's never going to be because, oh, magnesium 2 plus is a noble gas configuration that's more stable. It's not exactly just in and of itself the stability of going to that configuration. It's going to that configuration, forming something else that's going to be the least energetically costly event that could take place, forming like a chloride ion or an oxide ion, and then the back attraction of those plus minus forces. So you have to factor in. And the reason why those ions form is the then subsequent electrostatic force of attraction they experience once they're ionized. So there'll be an interesting picture we put together once we get into chapter 8, maybe today, if not on Friday, on why certain types of charges predominate for certain elements. Now, let's look at the left to right trend. You might have been, if you were looking carefully at the previous table, you might have been thinking, maybe you noticed this trend that as you go from left to right, we have the increase in ionization energy, and then we kind of decrease and then go back to an increase, then decrease, then increase. And if you notice, that's kind of the theme across the periodic table. If you look at the lithium beryllium group, we get an increase from left to right, and then we get a decrease to boron, then an increase, then a decrease, and an increase. So why do we have this pattern of general increase of ionization energy from left to right, but with this periodic trend or periodic inconsistency where the NP1 and the NP4 groups are slightly lower than you might have expected? So the left to right trend, we get the ionization energy increases, and now the increase should generally make sense. What happens from left to right is our effective charge goes up and our size goes down. Both of those trends point towards a greater energy of attraction of the valence electron to the nucleus. So as we're going from left to right, if we're thinking kappa Q1, Q2, divide by D, that's our energy of electrostatic attraction. I usually think of the magnitude of this because you get the plus minus. So the plus of the nucleus, the minus of the electron, makes for a negative energy of the electrostatic energy is negative, but think about the magnitude of that energy. The magnitude of that attractive force is going to increase as we increase the effective charge. So if the effective charge goes up from left to right, that makes the attraction go up. And then if the size drops, that also makes the energy of attraction, the magnitude, go up. It makes it more negative, but that makes it a greater magnitude. So if we have something like fluorine or neon, where we have a really small atom that has a really high effective charge, it's going to be that much harder to remove an electron from those atoms. So the right side elements have really high ionization energies because they're small and they have that high effective charge. So to go to F plus or go to neon plus takes a tremendous amount of energy. And that in and of itself isn't why we don't see fluoride cations and neon cations. It's then a question of, well, what could the electrons do to something else? We'll see in the electron affinity case, there's really nothing for the electrons to do to other atoms. Like the metals don't want to absorb electrons. There's no real benefit to them absorbing electrons. And then what we're going to see is the sort of issue on which elements go plus versus which go minus, or a 2 or 3 part problem of which electrons have the lowest ionization energies. That's the metals. So they cost the least amount of energy to ionize on the periodic table. And then the other questions are, well, how much energy do you get back when you make the anions? We'll see that's electron affinity. We'll see that in a minute. That the right side elements usually give us energy back when they make anions, and then you get the plus minus interactions, electrostatic forces from there. Okay, so then why do we get this periodic inconsistency though? So why do we have the breaks in the configuration with this periodic inconsistency in the MP1 and the MP4 group? Well, it's simply that our ionization is looking at the highest energy electron or the largest electrons being ionized. And as we're going from lithium, so if we're going from lithium and beryllium, having their nuclear charge, 1s configurations followed by the 2s, we have the 1s, then the 2s configurations. Think about how then boron has a larger 2p. So boron's kind of interesting in that instead of it removing an electron from an s subshell, it's removing it from a p subshell, which just happens to be a slightly larger subshell than the s subshell. So I call this a configuration anomaly. So as you're going from left to right, lithium and beryllium are losing s electrons, boron's losing a p electron instead. And so the energy associated with a p electron just a little bit lower on average, despite the relative size difference and effective charge difference for boron. So it's just removing its electrons from a different type orbital. So that's where we get our inconsistency from. And then why is oxygen a little bit different? So the difference between boron and oxygen, boron's configuration is a 2p1. So 2s2, 2p1. And if we get all the way to oxygen, put oxygen in red. So oxygen gets all the way to this configuration where it spin pairs an electron. So oxygen is slightly different than boron, and it's removing a spin paired electron. Spin pairing causes increased repulsion that we're breaking by removing the electron. So it was a little bit more costly to put the spin paired electron into oxygen, so it's a little bit easier to remove it. But then we get the fluorine and neon. They also have spin paired electrons, but that are closer to the nucleus, experiencing a greater charge. And we go right back to our trend of increasing ionization energy. I don't want us to focus too much on the periodic break. What the issue here is that if our idea of ionization energy is it's a way to measure or consider the valence electron's attraction to the nucleus, it's just not a perfect way to compare that from left to right. we have lots of things going on from left to right, not just the general idea of valence electrons attraction to the nucleus. We have different types of orbitals. Some of them are spin paired, some of them aren't spin paired. So there's not a clear comparison from left to right on size versus attraction. There's a lot of other things that go on too that factor into ionization energy. If we just said, generally speaking, left to right, are electrons more attracted to a smaller nucleus with greater charge? Yes. Are there some configuration issues that get in the way of measuring that or putting numbers to it? That's where ionization energies kind of get in the way, where they're just a slightly imperfect way to consider charge from left to right. One last thing that hopefully this isn't too confusing, but as you go from left to right, if you're looking at like lithium versus boron, carbon, nitrogen, oxygen, that all of those elements still have 2s subshell electrons. You could measure experimentally the energy to remove the 2s electrons instead of just whatever the highest energy electron is. And from left to right, the 2s electron removal increases without any inconsistency. So it's just a configuration anomaly. So it's just a configuration issue from left to right that we get an inconsistent type of configuration from left to right or type of orbital we're removing electrons from that leads to our weird zigzagging trend, but with general increase in IE from left to right. Now what about top to bottom? Well, you can kind of see from top to bottom, the noble gases show a good trend. I mean, all of the elements are showing a drop in ionization energy from top to bottom. Now, the top to bottom trend is actually kind of tricky because we have two things going on at once that make it hard to predict what we might have expected. We know from top to bottom that the size here, that if we're thinking top to bottom, the atomic size is increasing. So chlorine's bigger than fluorine. That puts the outer valence electron further away from the nucleus. That should make it easier to remove. That should reduce the ionization energy. So we'd expect that this change here should lead to a drop in the ionization energy. But then the effective charge slightly increases. And that's where picturing the Z effective being a very small, but a increase in the effective charge. So we get the slight increase in effective charge from top to bottom. That would predict a slight increase in ionization energy from top to bottom. So the effective charge would say, well, the ionization energy should go up from top to bottom. Well, it's kind of a question of, does the size become larger or does the effective charge increase? Which one of those increases is by a larger magnitude? And it must be the size increase that generally wins out because we get the general decrease in ionization energy. So again, we might have had a hard time predicting what do we expect knowing nothing about ionization energy. If we didn't know the trend, if I didn't have this chart up and just said, what do you expect for ionization energy? You may have said, I have no idea. One trend says it should decrease, one said it should increase. I have no idea how to consider. But think about how from top to bottom, size is increasing by quite a bit. The effective charge increase is a small increase. There's a few elements, like here, where mercury is higher than cadmium, where you get a break in those elements trends where you can say, well, it must be for the mercury that its effective charge was a bigger difference than its size increase. So there are a few cases, there's a few elements where you can see like lead's a little bit higher than tin. So there's a few elements that actually increase from top to bottom, and you can reason out for them it must be that their charge difference, their effective charge difference was just a greater magnitude difference than their size difference. There's not a lot going on that I want to talk about in terms of left to right IE trends across the transition metals. You get a slight increase, but it kind of zigzags a little bit. There's a lot going on there that's not worth talking about here, so I just wanted to briefly mention that generally you get a slight increase from left to right across the transition metal series, but there's some zigzagging, and I wouldn't worry about why that is. And what leads to the specific nature of those ionization energies isn't something we're dwelling on. Just a general increase from left to right with that periodic inconsistency with our main group is kind of the focus. And then our IEs tend to decrease slightly as you go down from top to bottom a group. Okay, let's get into the configurations of ions. We mentioned in chapter 6 that all those configurations were for neutral atoms, that in the next chapter, this one here, that we would talk about configurations of ions. In some cases, ion configurations are exactly what we might expect. So we're going to lose electrons first from whatever orbital happens to be largest for the atoms, and it's not always in the same order as the electron configurations. For some atoms it is, but for some atoms it won't be. So let's take a look at calcium. And then in general for electron configurations of like calcium 2+, sometimes it's easier to start with the neutral atom first. So it's usually easier to kind of consider, well, if we want the configuration of calcium 2+, let's make sure we picture calcium neutral first. Calcium comes after the noble gas argon. It's a 4s2. So we have n equals 3 shell electrons, then the n equals 4. So the largest shell here is the 4. So we will lose for calcium in the order we fill the electrons in. So we will lose the 4s2 electrons first to go to calcium 2+. And so, of course, this is just the argon configuration. So for calcium, exactly what we would have expected. Titanium and iron, we're going to see, require us to think a little bit about the relative size of orbitals. We were getting at this question when I asked for, I think it was for titanium, but there was a question in chapter 6 where I asked the question, well, which of its orbitals is the largest? And it maybe wasn't the one you thought it would be. So for for titanium, it would be the argon configuration nearest preceding noble gas, then a 4s2, then a 3d2. And we were talking about here in chapter 6, if you recall, that the 3d subshell is actually smaller than the 4s because the n equals 4 shell is all larger than the n equals 3 shell. And then in terms of like orbital speak or like where are these orbitals relative to each other? Well, we have our nucleus of 20 plus. We have the 1s2, the 2s2, the 2p set of orbitals, the 3s2, the 3p set of orbitals. And then we have the 4s here. So this would be the n equals 4 orbital. And then we'd have the 3d would actually be back into this space here. So the 3d orbitals would be in the space within the n equals 3 row, in the space near the 3s, the 3p, and the 3d. So our orbital size would go kind of like this. The orbital size will always go like 1s is the smallest, then our 2s, then our 2p, then the 3s, then the 3p, then the 4s, then, let me continue to the 3D. So the 3D would be here, and then we're continuing from the 3D, then the 4S, then the 4P, then the 4D, then the 4F. So the orbital size just kind of goes in this direction here, which if you notice wasn't the order that we filled electrons into the subshells. Like we were filling into the 4S and then filling back into the 3D after, but the 3D is still smaller than the 4S. Okay, and so the largest orbital here is the n equals 4, is that 4s2. So if we remove electrons by rule from the largest orbital first, then the configuration of titanium 2+ should lose the 4s electrons and be an argon 3d2. If you notice, you might have expected it to be a 4s2. You might have thought, well, why wouldn't it lose the 3d? I last put the electrons into the 3d. Why don't I remove those first? Well, it becomes a tricky question. It becomes a tricky question of, well, which electrons are further away? The less attracted electrons in the nucleus are further away. So it becomes a kappa Q1, Q2 divide by D problem. Further away, lower attraction, easier to remove. It also kind of shows that for calcium, if you think, well, what's the difference between calcium has 20 electrons, like titanium 2+ does, and calcium's configuration, neutral, is 4s2. The difference between calcium and titanium is an extra 2+. You can think, for an atom, if I have an 18 plus charge, however much charge makes it out to the outer 4s shell, not much. But the question is the 4s, do I want to get near the other electrons I have repulsions with? Or do I want to go further away? Calcium's like, I'm going further away. There's not enough charge to pull me in to be near those other electrons because I experience too high of a repulsion. Titanium 2+ says, hey, what if I give you 2 more protons? What if I get a little bit more charge? Then they're like, all right, we're in. So the 3D electrons say, okay, we can fill into the 3D subshell just because you have the greater charge. So when we have cations, we have a higher overall proton count, so we can fill electrons on average into the subshells that are closer to the nucleus. Now this is just a general rule for cations. This isn't like an anomaly. So the general rule for cations is we have to think of the configuration of the neutral atom and just consider which subshell of those electrons are largest. Let's lose in the order of size the largest first. So then if we need to lose 2 more electrons to go to the configuration of titanium 4+, then we think, well, the next subshell would be the 3s, 3p, 3d, 3d the largest of the n equals 3 shell, so we then lose the 3d. So titanium 4+ is, of course, just the configuration of argon. Titanium 2+ would be that 3d2. Iron, the other noble gases have this probably more commonly because the larger transition metals often don't lose all their electrons. Titanium 4+ is a very common cation for titanium. Titanium 2+ actually isn't all that common for titanium. But for iron, 2+ and 3+, very, very common cations for iron. Iron's configuration, of course, would be an argon, followed by a 4s2, and then it's 6 across, it's a 3d6. And so then what about iron 2 plus? Are we losing the D first, or are we losing the S first? By rule, we got to lose the largest 4 shell first, so we lose the 4s2 first. So iron 2 plus would be an argon configuration followed by a 3d6. A quick double check should be iron's element number 26. So we should have 24 electrons assigned. So iron 2 plus should have 24 electrons. So you could double check 18 plus 6 is 24. So you can double check your electron count to make sure that you have the proper count for the cation. If we need to lose one more electron for iron 3 plus, then we're going to take then one of the D shell. So iron 3 plus is an argon 3d3, or I'm sorry, 3d5, because one more out of the 3d subshell. So first 2 from the 4s, we need to lose a third from the 3d. So we're just losing electrons in order of their orbital sizes from the largest orbital first, because the largest orbital experiences the lowest overall attraction. It's the easier electrons to remove for an atom. Anions are actually pretty easy. They just follow along our configurations. We're just putting electrons into the next shell of, or into the next open subshell. So for oxygen's configuration, we know it's a neon. We'll just go from scratch. 1s2, 2s2, 2p4 for a neutral oxygen atom. Add an electron in, it just goes right where you would expect, right into the 2p subshell. So O minus would be a 1s2, 2s2, 2p5. If we're thinking of a diagram for oxygen, 1s2, 2s2, and then if we're thinking first from the 2p4, of course we're just filling in a fifth when we go to the O minus, and then filling in one more to go to O2 minus. So this is just a 1s2, 2s2, 2p6. The configuration is exactly the one you would think for anions. So I just want to make sure that we see for anions, nothing funny going on. We're just simply filling in to our open subshells. Now, once you get to a noble gas configuration, the energy of the next subshell is a lot higher in energy. So to pack an electron into argon, to go to argon minus, not going to be very likely that this takes place, because we already have the neon configuration, 3s2, 3p6. So argon's configuration, of course, would just be if it formed neon, 3s2, 3p6, and then into the 4s1, just filling into that next subshell that we would have expected, kind of just like potassium or calcium's configuration. And then that configuration is going to be a lot higher in energy. It's going to take a lot of energy to put an electron into a higher energy subshell. Now for oxygen and for anions that go to O2 minus, you may wonder, do we get energy back, or does it cost energy? It actually costs energy to make O2 minus. You know, like when we start thinking about, configurations that we teach you in chapter 2 and ionic compounds, when we say, oh, the noble gas configurations are more stable, it's really that they're more stable once they form, because they're going to be the best out of all the other options they could have done. Even though it actually costs energy to make O2 minus, it takes energy to make magnesium 2 plus or cations, but then once they form, they get that negative positive interaction. That's where the driving force comes from forming those compounds, and then that energy in total being the most negative out of all other combinations. Okay, so anion configurations just follow along from the periodic table in our ordinary configurations, and then cations just lose electrons in order of largest n. The largest orbitals lost first. Now, one thing I wanted to point out for the largest orbital should be the largest n with whatever the largest L is. Let's look at one more case. Let me add a slide here just to look at the case of something like tin. So let's consider the configuration of tin 2 plus real quick, just to look at that highest n with the highest L problem, just to make sure we see how we can identify the largest orbitals. So if we're looking for the configuration of tin 2 plus, I would recommend start with tin neutral. So neutral tin, it's element number 50, so that's the proton count. So we should have 50 electrons for tin neutral. So that would be kryptons, the preceding noble gas. We're filling into the 5s2, go all the way across the 4d10, and then we finally arrive back at the 5p. And again, carbon's a 2p, silicon's a 3p, germanium's a 4p, tin's a 5p. If you're confused on how do I remember if it's a 4p, 5p, or 6p here, it's just the 5. And then of course this is just a 5 as well. And then this shell here is one lower as the 4d. Now with all of this, if you go back to valence count, sometimes it's helpful to see that our valence count was 4. And so those should be the electrons we consider removing. The valence electrons should be the outermost electrons, highest n. And so then the largest electrons should be the highest n with the highest L. So do you notice it's not just the highest L. The highest L here is the 4d. That has an L of 2. But the issue is we'll look for the highest n value, which is 5, and of those, which has the highest L? Well, that's the p. So this has an L of 1. This has an L of 0. The 5p is going to be larger subshell than the 5s. Now you could get there from what I was saying before, that the s is always smaller than the p, smaller than the d, etc. So there's a lot of ways that you could have predicted or known that the 5p was the larger subshell, but we lose the 5p first, so 10's 2+ configuration should be krypton, 5s2, 4d10. And then if we said, well, what about 10-4+? What about that cation? Then we just lose then the next largest electrons, the 5s. So 10-4+ would just be a krypton configuration followed by a 4d10. So I just want to make sure to highlight that you can spot the largest subshell, the highest n with the highest L. Definitely think of the neutral atoms configuration first. That helps you spot which orbitals have, and to consider their relative sizes. And then just remove from the largest orbitals first. So electron affinity is our last kind of topic for chapter 7. We're only covering through section 4 in chapter 7. I do have a couple slides out of a few of the later sections just because there's one little trend I'll show you from the later sections before we move on into chapter 8. But electron affinity is the energy associated with absorbing an electron. And so the so it's the energy associated with absorbing electrons. This chart here is the EA1 chart, the energy associated with absorbing one electron for each of these elements. So if you compare like oxygen and fluorine, for example, so oxygen's EA would be oxygen absorbing an electron, and it's gaseous oxygen, just like our ionization energies were for gaseous atoms, going to gaseous oxygen minus, and you see that the electron is, it's more stable, it's negative, it's down, that's good. That means that the electron experiences a lower energy in the shell of an oxygen atom than it would have as just a free electron. So if you're taking, let's look at fluorine. So fluorine, more negative because, well, let's think about why. Why would fluorine be more negative? Fluorine's minus 328, more favorable for fluorine. Well, fluorine compared to oxygen, fluorine's smaller, that's good. Fluorine has an open spot for electrons, that's good too, because we need a shell in the n equals 2 shell to put the electron. And then we need a high charge. The effective charge is higher for fluorine. So that's good. So fluorine's great. Fluorine's the best at this, or almost the best at this, because it has an open valence shell in the shell to put the electron into, so it doesn't have to use a higher energy subshell. Then it has a high effective charge. That's good. And then it has a small size. Very, very good. Now, why are the noble gases so bad at this? Why are the noble gases, like, they don't even have an energy associated that's been measured because they don't want the electron. It's hard to measure the electron because it's an unstable configuration. The electron just falls right back out before you can really measure the relative energy. The noble gases are positive because you've got to throw it into the high energy subshell. So neon doesn't have a spot in the n equals 2 shell. It has to put it in the n equals 3 shell. That takes a big jump in energy, and that's very unlikely to take place. So we don't get stable ions for neon minus, argon minus, et cetera, as we would have expected. Okay, so the noble gases kind of reset the trend. They're the worst. They have the highest electron affinities, and then we become more negative. So this trend is actually becoming more negative towards the halogen group, generally from left to right, and then it resets with the noble gases. So the noble gases are the group that reset as the highest, and then we're decreasing from the noble gases across from left to right back towards the noble gases. Now, the top to bottom trend is kind of interesting. The top to bottom trend, again, kind of comes back to a trend we can't easily predict, because if we think energy of electrostatic attraction, kappa Q1, Q2, divide by D, if we're comparing fluorine and chlorine and kind of saying, should we expect chlorine to be more or less negative than fluorine? We have a problem, because for chlorine, its size does go up, and that should decrease the energy of attraction of putting the electron. So putting an electron in chlorine shouldn't, by just the size comparison alone, would say, well, chlorine's bigger, the electron shouldn't be as attracted to its nucleus. But then you say, oh, but the nucleus is slightly more positively charged. And then we have this weird issue of anions grow larger than their neutral counterparts. So it becomes a really complicated question of, like, what's the difference between F minus and F's relative size? What's the difference of Cl minus versus Cl's relative size? What's the difference of effective charge? Where the effective charge says we should get a slight increase in ionization energy. And for whatever reason, the third row seems to win out. So if you notice, the third row, it just happens to be more negative than the second and the lower rows. I don't think we ever would have predicted this. But it just, I don't even think it's that big of a deal, though. I don't think it's that important to think about, other than we have an interplay of two trends, or maybe three trends, where the two trends are effective charge and the size trend oppose each other in our prediction. And then we also have the relative size difference of F minus versus F. So we have the issue of, well, how much bigger is F minus compared to fluorine versus Cl minus compared to Cl? And it somehow turns out that the third row wins out and was the best. So the third row, generally the most negative. The top to bottom trend, I usually say there's not much of a trend going on, even though there kind of is. There's something there that's interesting. It's just not that big of a deal. You know, so the biggest deal, I think, to think about, most negative towards the halogens, because they're generally from left to right the smallest element that have room for one more electron. So the halogens being the most negative makes a lot of sense. And then if you also notice, we get another periodic issue of, in this case, it's the NS2 configuration is a little bit more positive than you expect, as is the NP3 group. And it's the same configuration problem, but in reverse. So we have a configuration problem here because beryllium, if it's going to absorb an electron, it has to put it into a higher energy subshell. So instead of, lithium putting it into an open S, it's putting it into a higher p orbital. So that takes a little bit more energy than you might have expected. And then nitrogen has to spin pair an electron. That takes a little bit more energy from left to right. So we have some configuration issues, just like we had with ionization energy. Again, I don't think this is that big of a deal. But if you're looking from left to right saying, well, why do I get the general decrease towards the halogens, but the beryllium and nitrogen groups kind of stand out as not fitting in? It's just because of that configuration anomaly or issue we were talking about, but in reverse from ionization energy. So we're getting this issue here with the NS2 and MP3 group. And again, I don't think you'll ever be asked about where's the weird inconsistency from left to right for electron affinity. It's not that big of a deal. But if you're looking at that saying, that seems like we should talk about that, I wanted to make sure to mention why it is we get this inconsistency with electron affinity from left to right. Okay, so with that, from the later sections, there's just one little trend I think is important to look at, even though we're probably never going to ask you about this on a test. But this is really interesting to point this out. And I think it's fascinating to see this, and I think it'd be crazy to not talk about it. Look at the melting point trends of our metals. Like, I don't know what you would have expected, but lithium, sodium, potassium, rubidium, cesium, almost everybody thinks melting points would increase from top to bottom. But they don't. The melting point actually drops. And cesium is actually almost a liquid at room temperature. Cesium's melting point's 28 degrees C. So take a sample of cesium. It's a pretty rare metal, but if you had enough cesium to have a sample of it, it's going to melt just above room temperature. So cesium was very, very close to being a liquid at room temperature. And it's kind of interesting to see that our metals are decreasing in melting point. So if we look at the alkaline group, same trend from top to bottom. Beryllium is actually the highest melting point. And I think it's really interesting to then contrast that and say, well, does every group decrease in melting point and boiling point? Well, hopefully you remember that, or you might remember bromine and iodine are liquids and solids at room temperature, so we have to have a reverse in the trend. If we look at chlorine, bromine, iodine, we get an increase in the melting point from top to bottom. So what's going on there? Like, isn't that interesting to see that our metals dropping in melting point from top to bottom, but our non-metals increasing in melting point from top to bottom? And I think it's a consequence of charge. Anytime we have charge that's being shared among atoms, it's easier to share charge when atoms are small. Plus, it's a Coulomb's law problem, that when the distance of separation is smaller, we get a greater attraction. So lithium and what metals are going to do, We'll see a model of this in chapter 12 is they're sharing valence electrons, they're sharing charge. It's easier to share charge when centers are small. It's harder to do it when the metals are bigger. But then when we're having to sort of induce a charge, when we have fluorines next to each other, two fluorine atoms, or fluorine molecules, F2s, two F2s adjacent to each other, they don't have built-in charges. There's like the nature of fluorine is that it's not exchanging charge across the entire structure, but how does it ever liquefy? Well, it has to somehow, the two fluorines have to somehow pair up and induce a dipole in themselves, and it's going to be harder to do that when the atoms are small. We're going to see when atoms grow bigger, it's easier to do that. So there's an important difference in molecular properties and molecular structure that comes about from whether atoms have built-in charges already or if they have to induce those charges, and you get the flipping. So I think it's kind of interesting to see that you get this reversal. The noble gases increase from top to bottom in melting point and boiling point as well, but radon's still well below room temperature, so radon's still a gas at room temperature. Oganesson, the OG, the 118 under radon that's not on our periodic table, that we should reprint this and have it there. But OG, the last element on the periodic table that's been discovered in atomic number, is predicted to be a liquid, but there's never going to be enough atoms to have a sample of that element. Its lifetime is just too short to exist for long enough to collect a sample that's on the order of grams, but it's actually predicted to be a liquid if it were able to exist. Okay, other than a couple of problems here, let's look at a couple of review problems out of chapter 7, and then we'll head into, well, I don't know how much time, probably won't get us started on chapter 8. Might say a word or two about chapter 8 before we wrap up today. But let's rank these atoms by increasing size. I guess it doesn't clearly say that. So let's rank these atoms by the increase in their size or their radii. Which one's correct? Or are both of them correct? Well, fluorine, lithium, sodium, how do we rank their relative sizes? So if we're ranking neutral atoms, that's atomic radii trends. So I'm thinking of the relative size of fluorine to lithium to sodium. I'm just thinking about my periodic trend from left to right. I know that lithium is going to be bigger than fluorine from left to right because size decreases left to right. And I know size increases top to bottom, so I know sodium's bigger than lithium from our top to bottom trend. And so it should make total sense that lithium is smaller than sodium, and then fluorine's even smaller than lithium. So that trend, I think, makes perfect sense. So that's the exact trend we would expect for those atoms. So trend 1 looks correct to me. What about sodium plus, F minus, and F? Is this trend correct? Well, here we're actually comparing isoelectronic and then going back to a relative anion versus neutral atom comparison. So these two, sodium plus, F minus, share having 10 electrons. So they're isoelectronic. And so the one of them with more protons, the 11 protons for sodium, should be smaller than the 9 protons of fluorine. So that makes sense. Sodium plus should be smaller than F minus. So it was actually our example on reviewing isoelectronic series. And then F minus versus F, what about this comparison? Is F minus smaller than F? No, anions are larger. We add an electron in, anions should be larger than their neutral counterparts. So this trend here would not be true. So it's F minus, it's bigger than F. Now, some trends we can't make. Like if I ask sodium plus versus F, can't really make a comparison. There's going to be some cases, isoelectronic, we can make an easy comparison. I can compare left to right neutral. Sometimes I can and can't compare the relative size of atoms. So this trend here, I don't think I could even put a trend to Na plus, F minus, and F. I just know this trend is wrong. So I know for sure trend 2 is incorrect here. So the only one correct should be trend 1. I think there's 2 more review problems in the notes here. Which atom or ion below has the greatest ionization energy? Which one has the lowest ionization energy? This is actually a tricky question because we're mixing in here cations and anions and with neutral atoms. So ionization energy is the energy associated with losing an electron. So we're asking which atom below, when they lose 1 electron, takes more energy. So let's write those ionization energy reactions real quick. So let's write F losing an electron. That would be going to F2 plus an electron. That sounds pretty hard. You know, just generally thinking of F to F plus is high, F losing a second electron sounds like that's going to probably take quite a bit of energy. So that seems like that should be a relatively high ionization energy step. If I compare that to F plus an electron, I can already rule out answer B, because answer A would be the second ionization of F. Answer A is the first ionization of F. I know the second ionization is always greater than the first. So I can already rule out answer B, because this is the I1. This is the I2 of fluorine. So second ionization of fluorine should require more energy than the first. Now, what about oxygen? Let's look at oxygen next, going to O plus an electron. The first ionization of O compared to F. F's higher. Like left to right trend increases. Our general increasing trend of ionization energy that increases left to right. This is the I1 of O. This should be less than the I1 of F, which we know is less than the I2 of F. So O is even less. If I'm ranking these in order, so far I'd have A should be the greatest, and then I know that it's greater than B. I know B is greater than D. So I know for sure if I'm just looking for the highest ionization energy, it's certainly not D. Now F minus, this is kind of tricky in a way, because F minus losing an electron, the ionization step is just losing an electron back to F plus an electron. And at first glance, you may be like, I have no idea how to make this comparison. Well, if you just think about it, F minus is huge. Well, relatively speaking, the F minus is bigger than F. So if F minus is larger, do you think F minus has a larger or smaller ionization than F? It's going to be a lot smaller. This actually has the smallest ionization of all of these. So this is the negative of the electron affinity of F. It's like the opposite of the EA step. EA is the atom absorbing an electron going to the anion. This is like the flip of the EA reaction. If you remember, that was like minus 328. So this would be plus 328 kJs. If you think of the magnitude of like B, the magnitude of the first IE of fluorine, it was like 2,000. So a lot smaller. So this is like the magnitude, we can actually put a number to this. It's plus 328 kJs per mole. That's definitely a lot smaller than it was for F. F's like 2,000, I don't remember what this is. If you flip back, it's probably around 2,000 or probably even higher kJs per mole. Certainly positive. So now for F minus, to lose an electron takes less energy than for F. So F minus bigger, F smaller takes more energy for F. F plus even smaller takes even more energy. F2 plus even more energy. So it becomes kind of a successive ionization problem if we think about it from the completely filled, even from F minus, should take less energy than F plus, etc. Okay, so our highest ionization energy should be highest with A. So F plus losing an electron should have the highest ionization energy. The lowest ionization energy, the lowest of these three, is going to be the F minus because it's the largest of them. It might be hard to compare it necessarily versus, if I'm comparing O versus F minus, it might be kind of tricky for sure to know this, but C is going to be lower because it has that negative charge, a lot bigger, easier to remove that electron. So we can kind of put an order to these, kind of rank order the magnitude we expect for our ionization. Let's go ahead and take our quiz here to wrap up. I think there's one more question from chapter 7. We'll look at whatever that last question is next time, and we'll end here today on our quiz. Keyword xenon.